Let's review some familiar sets, or maybe not so familiar sets, that might come up throughout the course. So first we have the natural numbers. And so depending on the book or context, it might mean the counting numbers starting at 0, so 0, 1, 2, 3, and so on, or starting at 1, right? So this actually depends on the book or context. And so in general, it's good to be clear about which one of these you actually mean when you talk about the natural numbers. In many contexts of counting, it's common to include 0 because when you're counting stuff, it's useful to have when there is nothing, right? So that the size is 0. And in that sense, if you're talking about counting the set of counting numbers, it might be natural to include the 0, right? Next, we have the integers. So the integers are, it's essentially the natural numbers with the 0 and their negatives, right? So these are the integers. You have the positive integers, which are the ones that are larger than 0, the negative integers, smaller than 0 and 0 itself. Next, we have the rational numbers. So the rational numbers, we saw them in a previous lecture, were the numbers of the form m over n, where m and n are integers and n is different than 0. And so that includes essentially all the fractions, right? But it doesn't include rational numbers. So we saw in a previous video that square root of 2, so we saw, for example, that square root of 2 does not belong to the rational numbers. It does, however, belong to the real numbers. So the real numbers are all the rational and irrational numbers. They're not as simple to define in the way that is written here, but you've seen them probably in your calculus course, in your algebra course, and maybe other courses. Defining them, you should do an analysis course, and you can then talk about defining them. The gist of it, or one of the ways to see, is that the real numbers, it's gonna be sort of the set of sequences, of sort of convergent sequences of rational numbers in some sense. But yeah, so go read an analysis book for that. But essentially the real numbers, you're accustomed to it as what you work like in calculus. And for example, square root of 2 is a real number. The constant e is a real number. Pi is a real number. And these are all real numbers that are not rational numbers, right? They're all irrational, and so on. You might have also seen the complex numbers. So the complex numbers are sort of, so one of the ways that you generally see them is through the complex plane. So you write it, so you have your first coordinate for your, so you have something like A here and B here. This is the imaginary line, and this is the real line. And your complex number is here. And it has, so it's sort of working in R2 if you've done the linear algebra, right? So this is like the Euclidean plane, but it has multiplication. You're able to multiply points in the plane, and it has this rule that the I squared is equal to -1, right? So this is the complex numbers. So it's the A plus B i's such that A, B belong to R, and by I here, it's a special number that has this property here. Then you have other, just as examples of sets that you've dealt with, there's also intervals in the real numbers. So it's common to denote this here by all the numbers, so the x's in R, such that x is in between A and B. And you have, for example, the closed interval, which is the same set but with less than equal, and so greater than equal and less than equal, right? So it includes, so when you think of the real line, and you have your point A here and your point B, so this would be the open set, not including A and B, and if you include them, this would be the closed interval AB. And then we also saw, when we were doing some proofs, we saw, for example, there was the even integers. And so what are the even integers? One way you can write it is in this way here, the 2k such that k belongs to z. So for every k in z, it's going to be numbers that you're multiplying by 2, right? And so, again, this is the even numbers. So it's 0, 2, 4, -2, -4, and so on. You also have the odd integers, which is just all the elements in z that can be written in the form 2k plus 1.